Greetings again, fellow lazy chemists. Today we are going to go ahead and work on calculating percent error. And this is because nobody gets it right. So percent error is going to be something that's going to be a fairly pervasive topic throughout the year because we're going to be doing a large amount of experiments that we can then check against the actual number. And we are going to want to make sure that we're checking and seeing what our percent error is. In addition to being able to check our work for accuracy and to make sure that we've been doing the procedure right, it also is a factor that factors into your end of course exam, in that figuring out the percent error will be something that's in your practical exam. Almost 100% sure every single document that I saw has some percent error question on it for your practical part, which is the part that you actually do the lab materials for. So without much ado, let's go ahead and start talking about percent error. And when percent error is done, it's pretty much certain that your answer should not be exactly what the answer of the answer would be if every single thing went right. There's always going to be some variables that end up getting messed up. And because there's a lot of variables in action with the human variable and the chances for little tiny things to get misstepped, you're going to have an answer that's going to be different than the actual value. So some of those things can end up being mismeasurement, a lack of purity in your reagents. Oftentimes, even when I get like the special chemicals delivered to the school, we're only going to have 95% pure, which means that we're going to have some error because we only have 95% pure. We don't have 100% pure. And then you're also going to have some actions that, maybe you mismeasured something. Maybe it was, another millimeter less or another millimeter more than you were supposed to add. And you could also have, a little bit of poor lab technique that could end up, causing some error that has to be reassigned. And in general, if you have a lot of percent error, so if your percent error ends up being really large, that's usually a sign like, oh, shoot, I probably need to redo this experiment because my data is all wonky. Whereas if you have a little bit, it's like, oh, okay, it seems like I probably did pretty good and I probably understood it. Now, as an example, just recently I saw a campaign that was talking about those mass gaiters, saying that mass gaiters were about as effective as no mask at all. And one of the things that they did was they ended up showing a chart that showed how the mask gaiters were no more effective at stopping coronavirus than wearing no mask at all. And when I actually got the chart that allowed us to go ahead and compare it, you'll notice that for this particular chart here, it's counting the relative amount of droplets that are released from a particular mask that's being worn. And then it has the different masks that are right here. And some of these are, really, really small and they have no range. And what you're seeing here, and what most of you have probably seen, are these. And these are called error bars. And the error bars indicate that there's some error in the measurement. And that's perfectly fine. We're allowed to have error in an initial measurement. But in the particular way that they were saying was that these fleece, in particular neck gaiters, were as bad as wearing no mask at all. And remember, wearing no mask at all means that you're going to have a relatively high droplet count. It's going to be higher than this is. But notice that it has a high error bar, okay? And because it has such a high error bar, that means that the actual value is likely, or the experimental value could be anywhere in between here. Okay? So that means that even if you see a news report, like there's something like this, you can take a look and see, oh, well, where are the error bars? And if I saw something where they were trying to compare, how a 4-ply cotton mask was really, really effective and a bandana was not, I would be like, okay, well, where are your error bars? And an error bar like this, that's a whole level of magnitude in comparison to what's being measured, indicates that they don't really have a good grasp on whether or not it's going to be effective or not. And obviously, covering your mouth with anything is going to be better than not covering your mouth at all, but that's something to watch out for, that these errors are going to be systematic in nearly every experiment, and that we should just get used to being able to see them and seeing how close something is to that. So without much further ado, we're going to go ahead and move on. And we're going to move on to the next step, which is that talking about the two different kinds of error. And in those errors, whether it's a positive or negative error. And the first error we're going to talk about is systematic error. And systematic error is an error that is built into the lab and there is nothing that the experimenter can do about it. So for instance, if you were given a sample of iron to determine its density and the sample wasn't pure iron, it would constantly and consistently throw off your values. So if I gave you lead and told you it was iron and you measured the density, every single time that you measured the density, your density values would be off. That's systematic error, okay? Whereas random error is going to be what happens when you have tiny little lab mistakes. And, these mistakes, they could be super small and not even procedural mistakes. It could end up being just the air pressure in the room was low enough that you had extra evaporation that day than you didn't have it the day before. Maybe the air conditioning went off during the night while you were allowing a substance to dry and it ended up gaining more water. Those are different things that could cause some sort of random error there. In the case that is used here is, you could say that you're stirring some water and some of the water splashes out, okay? That's going to end up changing and that's going to be a tiny random error. Okay? A positive error is when you get a error value that ends up being greater than the actual value. So for instance, if you measure the concentration of a solution to be 2.5 molar and it's only 2.2 molar, that would be a positive percent error. And then a negative percent error is going to be when you have it go the opposite way. So if you find that the concentration is lower than you should have, that's going to be a negative percent error. Okay. Now you can calculate percent error in a fairly easy way. What you're going to do is you're going to go ahead and take your observed result, so what you got, what you measured, minus your actual result, okay, or what the actual number should have been, and then that's going to be divided by the actual number, okay, and that will give you a decimal, and then you know that to turn a decimal into a percent, you multiply it by 100%. And you're going to use this often in lab, and you're also going to try and explain it each time. So if you have like a positive or a negative error, you're going to want to try and explain it each and every time and try and find something that you could have done better or something that was wrong, or you're going to find some sort of error that you think may have happened beforehand that could account for your error. Okay, so here we go. We have an example. A lab group was working in a lab to determine the percent of magnesium in a sample of magnesium oxide. They determined that by weight it should be 58. They determined it was 58.3. Then they looked up the actual value and found out that it was 60.3. What is their percent error? And I want you to go ahead and try and use that now I'm going to go ahead and give you 5 seconds to work on that, and you can pause the video here if you want to work on that. Or if you want to just go ahead and continue on and wait those 5 seconds. Okay. So, observed was what they got. So they got 58.3. They have to subtract the 60.3, divide by 60.3, and they get 0.00331 times that by 100%. Funny math, funny math. Alright, give me just 1 second here because we had a percent error in our percent error. Okay, now that's the correct amount here. Once we go ahead and take -2 divided by 60.3, we should get -0.331, and that's going to end up being -3.31%. Okay, and that's all that percent error really is. It's just taking that observed minus the actual divided by the actual. So it's finding out how much error you have and dividing it by what the actual number was to kind of normalize it there. Okay. This next one, a different group got doing the same lab got a value of 68.6. What's the percent error? You'll do it the same way. 68.6 minus 60.3, that'd give us 8.3. That's going to be 0.1376, which would give us 13.76% error. Okay? And there's not really... And then we look to see what possible errors there could be. The mass of magnesium oxide could have been measured incorrectly. That's probably going to be your most common one, measurements incorrect. Or you could have lost some product, it could have fallen on the floor or something. That would have been another problem. If there were impurities in the sample, that would have caused it to go off. Or if the scale was miscalibrated, which unfortunately in our labs, is probably going to be the case. Okay. You will always have an error page in the labs that we deliver, and just make sure that you're recording it honestly. If there's an error, just record where it could have gone. If somebody sneezed and you lost half your product, you report that they sneezed and you lost half your product. Okay, that's going to close us out for this lecture. And you should be able to take the quiz at the end of this one.